The night sky is a river of static. Every star, every galaxy is a fixed point of light, a silent, unmoving reference. And against this vast, static backdrop, a few things are in motion. Finding them is the great challenge. It is not an act of human patience, not anymore. It is a job for a machine. This is the work of automated sky surveys, like the Asteroid Terrestrial Impact Last Alert System, or ATLAS. These are not the giant deep space telescopes built to study a single, distant galaxy. They are wide-eyed sentinels, robotic systems designed to scan the entire visible sky night after night with uncompromising digital precision. The process is a relentless high-speed subtraction. A telescope like ATLAS stares at a patch of sky and takes a picture. It waits 15 minutes, a half hour. Then it takes the exact same picture again. Software then takes these two images and digitally subtracts one from the other. In a perfect static universe, the result would be an image of pure, empty black. Every fixed star, present in both frames, would be canceled out. But our universe is not static. Anything that moved in that 15-minute window, any asteroid, any comet, will fail to subtract. It will leave a single residual point of light. The software takes a third image and a fourth. If that point of light appears again and again in a straight line, the algorithm flags it. It has found a tracklet. This is not a moment of discovery. Not yet. It is a data point. On any given night, a survey like this generates thousands of such tracklets. Hence, 9% of them are mundane, known asteroids, fragments from the main belt, orbital debris. The system's first job is to check this new tracklet against the master database of all known objects. Usually, it finds a match, but sometimes it doesn't. A new uncatalogued object has been found. Its position, its brightness, its time of observation, a tiny string of data is automatically formatted and sent, with thousands of others, to the one place on Earth that acts as the global clearinghouse for all moving things in our solar system, the Minor Planet Center. The tracklet, a tiny string of data from the ATLAS survey, arrives at the Minor Planet Center, hosted at the Harvard-Smithsonian Center for Astrophysics. This is the central nervous system. The MPC, operating under the International Astronomical Union, is the single official global body responsible for this. Its automated systems take in thousands of such reports nightly. The first, digital-only step is triage. The tracklet is compared against the database of millions of known objects. A match is found for 99.9% of them, but this one finds no match. It is new. The system flags it. The software now attempts to calculate a preliminary orbit based on just those few closely spaced observations. This first guess orbit is fraught with error, but it provides a critical clue. The orbit looks strange. It's not a gentle, nearly circular path like an asteroid in the main belt. It's highly elongated, highly eccentric. The system, or a human analyst, flags this as unusual. The object is not just new, it is interesting, and it needs to be confirmed immediately. The object is assigned a temporary designation, and its data is placed on a page that is one of the most vital, high-stakes forums in all of science, the Near-Earth Object Confirmation Page, or NEOCP. The NEOCP is not a press release. It is a bulletin board, a call to action for the entire global astronomy community. It is a public list of unconfirmed objects that need immediate follow-up. An astronomer in Arizona, finishing their night's work, checks the NEOCP. A team in Chile, just starting their night, does the same. They see this new high-priority object. They see its coordinates. They see the strange preliminary orbit. They know the clock is ticking. This object is faint. If it isn't observed again tonight and tomorrow night by other telescopes, its new tenuous orbit will be lost. The error bars on its position will grow so large that it will become a ghost, a one-night stand, lost back to the digital noise. The discovery, made locally by Atlas, has now been handed off. It has become a global hunt, a race to get more data points before the Earth turns and the object slips away. The handoff is complete. The Earth has turned. The original Atlas Observatory in Hawaii is now in daylight. An astronomer in Arizona, having seen the NEOCP alert, has pointed their telescope at the object's predicted coordinates. They find it. They capture a new set of images, a new tracklet. This new data, just a few hours after the first, is sent back to the Minor Planet Center. Then, as night falls over Chile, a larger telescope, the VLT perhaps, is brought online. It, too, finds the object, now fainter, but still moving. It sends its data. The MPC now has what it needs. Not just one set of observations, but multiple sets, separated by hours and geography. The observational arc has been extended from 1 hour to a full day. This is the first critical threshold. The initial 4-point orbit from Atlas was a guess, but an orbit based on a 24-hour arc is a calculation. At the MPC, automated software and human analysts run the numbers. They perform a least squares fit, an algorithm that tries to find the one unique path through space that connects all these observations. The software tries a simple circular orbit. It fails. The points don't fit. It tries a long elliptical orbit, like a normal comet. The points still don't fit. The computer must keep stretching the orbit, making it more and more eccentric. It finally finds a solution. The orbital elements flash on the screen. The most important number is eccentricity, E. An eccentricity of 0 is a perfect circle. An eccentricity between 0 and 1 is an ellipse, a bound, returning object like Earth or Halley's Comet. An eccentricity of exactly 1.0 is a parabola, an escape orbit. The number on the screen is not 0.8. It is not 0.9. It is greater than 1. This is the moment the world changes. An eccentricity greater than 1 defines a hyperbola. It is an open, unbound path. It is the mathematical proof that this object is not one of ours. It did not originate in our solar system. It is, by definition, interstellar, but this is a preliminary verdict. The error bars are still too high. The eccentricity might be 0.02, but the margin of error might be 0.05. It is statistically unbound, but it could still be a very energetic, parabolic Oort cloud comet that has been mismeasured. The verdict is not in. The hunt is now on, with a new critical urgency. Then EOCP priority explodes. This is no longer a curiosity. It is a potential scientific revolution. The number on the screen is tantalizing. Eccentricity greater than 1. But in science, a number is meaningless without its margin of error. The initial calculation, based on just 24 hours of data, might be is C our 1 moyas on $2, but the uncertainty is high. Perhaps an $0.05. This means the true value could be sign 7, a bound object. The verdict is not in. This is the moment a curiosity must be transformed into a certainty. The call goes out again, but this time with maximum urgency. This isn't just a follow-up, it's a confirmation campaign. The largest telescopes on Earth, Keck, Subaru, the VLT, are now mobilized. Their immense mirrors are needed not just to find the object, but to get astrometry, its precise position, with a vanishingly small margin of error. For the next week, a disciplined global effort is sustained. The observational arc, the length of time over which we have data, grows from 24 hours to 48 hours. The new orbit is calculated. The error bars shrink. Eureka. Describing 1:00:02 p.m. 0.03. The number is holding, but the uncertainty still grazes the 1.0 line. Another night. More data. The arc is 72 hours. Gisir 1.019 RPM 0.005 DSTR. The data points are converging. The algorithm, the least squares fit, is settling. Then, after a full week of observations from a dozen observatories, the final calculation is run. The observational arc is long enough. The precision is high enough. The new definitive orbit appears. Eccentricity 1.018 RPM 0 to 0.000. This is the moment. The error bar is now a tiny, tight bracket that is entirely above the 1.0 threshold. There is no ambiguity. There is no statistical doubt. The object is unbound. It is interstellar. The Minor Planet Center now has the authority to act. They issue a formal Minor Planet Electronic Circular, an MPEC. This is the official scientific birth announcement. The temporary designation is made permanent. The object is given the I designation for interstellar. Following Oumuamua, 1I, and Borisov, T2I, this visitor becomes 3I Atlas. The verdict is in, and it is hyperbolic. The hunt is over, and the real science is just beginning. Now, with a solid, predictable orbit, we can aim our best tools. We can point Hubble, we can point JWST, we can calculate with certainty that its path will bring it to Mars on October 3rd, 2025, and to its perihelion in late October. The tracklet has become a target. The verdict is in. Interstellar. The orbit is hyperbolic. But to truly understand its journey and to plan for its arrival, a 1-week observational arc is not enough. The future path is set, but the cone of uncertainty is still too wide. To narrow it, we must do the impossible. We must find this object in the past. We must conduct a precovery hunt. This is one of the most powerful tools in modern astronomy. We now have a solid hyperbolic orbit. This orbit is a key. We can use it to run the laws of physics backward, calculating precisely where in the sky this object should have been 1 year ago, 5 years ago, 10. We can generate an ephemeris, a list of past coordinates for an object no one knew existed. Scientists now turn to the digital archives. The Pan-STARRS survey, Catalina, even Atlas itself, have been imaging the sky for years. Their archives are petabytes of data, a digital time capsule of the night sky. A search algorithm is now tasked. Go to the Pan-STARRS archive for October 2022. Look at these exact coordinates. Is there a faint, uncatalogued dot of light?
The orbital parameters load.
The algorithm churns through terabytes of old images. It subtracts frames, hunts for residuals, just as Atlas did. But this time, it is not a blind search. It is a targeted assassination, and it gets a hit. On an image from 3 years ago, a single faint smudge is found, exactly where the backward-running orbit predicted. It was ignored at the time, just another bit of digital noise. But it is the key. This precovery data point is a lever. It extends our observational arc from 1 week to 3 years. A new orbit is calculated, now anchored by points in time, separated by years. The result is an orbit of astonishing, razor-sharp precision. The eccentricity is no longer 1,018 dash referees in Ornar. It is now 1.074 p.m. The cone of uncertainty for its future path collapses. We no longer know its Mars flyby path within thousands of kilometers. We know it to within hundreds. We can now tell the MAVEN mission planners exactly when and where the comet's coma will be. We can tell the HiRISE team exactly where to point to get a high-resolution image of the nucleus. The Precovery hunt, by finding the ghost in the machine, has solidified the future. The transformation is complete. A single anonymous 4-dot tracklet, flagged by a robotic telescope, has been passed through a global discipline system. It has been confirmed, its orbit deemed hyperbolic, its past found in digital archives, and its future path calculated with exquisite precision. The International Astronomical Union and the Minor Planet Center now bestow its official permanent name, 3IB Atlas. The 3I designates it as the third confirmed interstellar object. Atlas honors the survey that captured those first critical photons. This designation is the starting gun for the real science.
What is it made of?
The global network of observatories shifts from finding it to understanding it. Hubble, JWST, and the entire Mars fleet, TGO, MRO, MAVEN, are now executing planned observation campaigns. The questions are no longer where is it, but what is it? The faint light is dissected, revealing its CO2 dominated coma, its green C2 glow, and the persistent strange anomaly of nickel without iron. Its motion is scrutinized, confirming the anti-tail is a geometric illusion and measuring the gentle but firm push of its non-gravitational engine. This is a coordinated, multi-wavelength, multi-planet investigation, and this is where scientific hygiene is most critical. We know the key events are in October 2025, the Oct-3 Mars flyby and the late Oct-perihelion. But we also know that starting around Oct-21, the Comet and Mars enter solar superior conjunction. They will be behind the sun. This means a data blackout. The press may report the comet has vanished, or that scientists have gone silent. This is not conspiracy. It is a predictable institutional delay. The Mars orbiters will be collecting data during this time, storing it, and waiting for the reappearance in December to transmit their priceless, clean data back to Earth. This gap is not silence. It is the time it takes to get the cross-check. This entire process, from a single faint tracklet to a fully designated interstellar target with a multi-year, multi-planet science campaign, is the unseen, disciplined framework of modern discovery.